This presentation is delivered by the Stanford Center for Professional Development.
All right. Okay, today we're going to continue with our study of convolution. And let me remind you of the star of the show and how we got there. So last time we introduced convolution in what I hope you thought was a natural way to answer a reasonable, natural question in signal processing. All right. So we talked about how do you combine two signals in such a way that their Fourier transforms multiply. So you're led to convolution by asking for the Fourier transform of a combination of f and g is the product of the Fourier transforms. Fourier transform of f times the Fourier transform of g. Okay? And what we found was that the combination was certainly not obvious, but actually quite, at least compactly written. So the answer was given by the convolution of two functions. I can either look at the convolution of g with f or f with g. It doesn't matter. The convolution is the integral from minus infinity to infinity of, I think the way, just to be consistent with how I wrote it last time, I believe, g of x minus y, f of y, dy. That is to say, if this combination is defined, if this is the way you combine f and g according to this integral, then the Fourier transform of the convolution is the product of the Fourier transforms, which is quite a remarkable statement. I mean, all these operations are not to be taken lightly. Certainly the Fourier transform is a complicated enough operation involving an integral from minus infinity to infinity, a complex exponential, all the rest of that stuff. This integral, although it doesn't involve any complex quantities, is certainly, again, nothing to be taken for granted. And the fact that you combine these two complicated operations and they combine in such a simple way is pretty impressive. All right? And not only pretty impressive, it's pretty useful. In fact, before talking any more about any general properties of the Fourier transform, let me give you an example of just this sort of thing in action. All right, so let me give you an example of this in filtering. All right, and I'm going to take a particular, I'm not going to spend a lot of time on this, but I just want to show you that I'm not making this up, because we're going to return to this. We're going to return to a lot of these ideas repeatedly throughout the course, and also examples, similar examples, and sometimes study them in greater depth as we go through the course. The example that I have in mind, though, to start with was one that I borrowed from a book by Briggs and Hansen on the discrete Fourier transform. I think I put this in the list of references that's on the website. And it's called something like the DFT and Owner's Manual. It has all sorts of interesting, it's very well written. It has all sorts of good examples and good problems in it. And the one problem they study is the problem, they use as an example actually of filtering, is the study of turbidity. Now, I think we actually had some people in earth sciences in the class at one point. I think I remember that. Anybody know what turbidity is? Anybody from earth sciences in here today? No, it's raining outside, so they couldn't come. All right. Turbidity is... Turbidity is sort of a study of, I don't know whether it's a measure of the clearness of water or the murkiness of water, but it has to do with measuring the clarity of water. And the idea is that particles are suspended in water and light scatters off of particles, and you sort of measure how light scatters. That's a measure of the murkiness. It's a measure of the more particles, the more scattering, and the more murky it is. And turbidity varies over time, and one of the problems is to study how it varies over time. All right, so they did a study. They presented the results of a study of the turbidity of, I even wrote it down here, the Yukon, the subglacial waters in the Yukon Territory of Canada. Okay, so you get a picture that looks something like this. I'll show it to you. So can we get a shot of that? You want me to put it here? See how that is. That's my hair. I'm thinking of getting a haircut this weekend, by the way, so this is the last you're going to see me in this furry state. All right, I'll step back discreetly. All right, so that's a picture of turbidity. Now, the scales here aren't so important. The horizontal scale is time, and I think it's over a period of months. And the vertical scale is turbidity, whatever that means. All right? Now, so you put sensors down in this very deep subglacial water, and you measure the murkiness of light using whatever scale and whatever techniques are involved, and it oscillates over time. All right? Now, in this picture, you see not much. All right? So you see a couple of examples. You see, it's better maybe just to look at the TV. Anyway, of course, you don't have a TV, right? Anyway, what you see is you see a generally periodic phenomenon, but you see a lot of jaggedness in there. Right? You see a lot of jaggedness in the picture. Okay? Ah, there we go. Okay. Ready? Very good. All right. So anyway, like I say, the horizontal scale is time. I think it's a period of months, and the vertical scale is whatever it is. And you certainly see a periodic phenomenon here, but it's noisy, or it's jagged. And you want to get rid of the jaggedness of this. All right? Now, the way to do this is, the way to get rid of the jaggedness, the way to smooth out the data a little bit is to do it not in the time domain as you see it presented, but to do it in the frequency domain exactly in the way that we were talking about. All right? So the first step in the analysis of this data or in the smoothing of this data is to take the Fourier transform. Now, in fact, the data is given to you in discrete form, so what you're actually taking is the discrete Fourier transform, and we're going to get to that shortly. But think of everything here as just sort of continuous, and think about actually taking the Fourier transform by whatever means you have. All right? And if you do that, you get a picture that looks like this. So this is a picture in the frequency domain. This is a picture of the Fourier transform of the signal. As a matter of fact, it's two pictures. The first picture is a set of frequencies going all the way out, and I'm only drawing the positive frequencies here. When you take the Fourier transform, of course, you have, for a real signal, you have positive and negative frequencies, but one's a complex conjugate of the other. All right? So actually what's being plotted here is the magnitude of the Fourier transform only for the positive frequencies. And you see it goes all the way out. All right? The high frequencies here, and this is just a section of it just showing the first 40 or so frequencies. All right? Again, high frequencies are what's causing the jaggedness. Just as in the same case with Fourier series, the high harmonics are causing the signal to oscillate quickly. Well, the same thing with the Fourier transform. Although the signal is continuous in although the spectrum is continuous, this is the same principle. High frequencies are causing sharp oscillations or rapid oscillations. All right, so what do you want to do to smooth it? The natural thing to smooth it is to just kill off the high frequencies. All right? Now, how do you kill off the high frequencies? You do it by multiplying, the simplest way of doing it is by multiplying by a rectangle function in the frequency domain. Okay? So you kill off high frequencies by multiplying in the frequency domain by a scaled rectangle function. That is to say, if the picture in the frequency domain is something like this, where the frequencies are going all the way out, then you just multiply it by a function which is 1, by a rectangle function, which is 1 up to a certain point, say a cutoff frequency from minus nu c to plus nu c. All right, let's think of that as the cutoff frequency, and then it's 0 outside that. All right? So you eliminate all frequencies below minus the cutoff range and above plus the cutoff range, and you keep the frequencies in between. All right? The other way of putting this is you are passing the low frequencies or eliminating the high frequencies, and so this is called a low-pass filter. It passes the low frequencies. Okay? All right, so if you do that, then in the frequency domain, the result is to take a rectangle function pi. I guess the way I've scaled it, I'd represent it as pi sub 2c. It has width, total width 2c, 2 nu sub c. Excuse me. Nu sub c is supposed to be the cutoff frequency here, times the Fourier transform of the turbidity signal, whatever you want to call that, t. Okay, this is Fourier transform of the turbidity. That's what it looks like in the frequency domain. What does it look like in the time domain? Back in the time domain, you take the inverse Fourier transform of this, or you ask yourself what convolution leads to the product of these two functions in the frequency domain, and we know what that is. So in the time domain, this is convolution. All right, it would be, I believe, 2 nu sub c sinc 2 nu sub c times t convolved with the original turbidity function, t, whatever you want to call it, capital T of t. All right? It's convolution in time, multiplication in frequency. And the result is to kill off, in this case, is to kill off the high frequencies. And I'll show you what the picture looks like. All right, I'll show you what the picture looks like for two cases. All right. One is if you keep, I think, the first 40 or so frequencies, and the other example, I'm going to show you the graphs in just a second, and the other I think is just if you keep like the first 10 or 15, okay? And you get two different pictures. All right, this is once again the picture in the frequency domain. The picture in the time domain looks like this. All right, so what you do is you carry out this multiplication in the frequency domain, then you just take the inverse Fourier transform, or you know what's going to what the result is going to be, so you just compute the convolution. It has to be computed numerically, of course. Everything here in sight is actually discrete data. All right, so in the first case here, this is, I think, only keeping like the first 10 or 15 frequencies, something like that. I can't remember exactly what they did. I'm sorry, I didn't have a chance to look it up this morning to get the precise cutoffs that they used. And this one is keeping maybe the first 20 or 30, maybe up to 40 frequencies. All right, so you see, you still have a certain amount of jaggedness in here. Here you see very quite strongly that the thing has been smoothed out, and you can see the periodic nature of it. All right. So this is an actual study, I mean, of an actual of actual data. By the way, they rescaled here. The scale on the vertical axis is different because I think they just subtracted off the mean, so they get it to oscillate around 0 instead of oscillating around whatever it was. That's why the scale is different here on the vertical axis. All right, now there's a serious question involved when you're applying these techniques to real data for real, where something real is at stake. Namely, you might say that let's go back to the original picture. There's a lot of noise in here that doesn't belong, all right? Somehow it's a consequence of our sensors or whatever, some result of faulty experimental technique that I'm getting all these extra jagged edges in there. Who knows why that's happening? So I want to filter those out, all right? And I can filter them out very dramatically, and to get this picture by only keeping the first however many frequencies, or I can filter them out a little bit less dramatically by allowing a certain number of high frequencies to creep in. And the question is, when are you filtering out something essential? And when are you filtering out just noise? That is to say, when are you presenting the real, genuine physical phenomenon to be understood and to focus on what should be understood, and when are you committing scientific fraud? All right? Each of us must answer this question in his or her own way, I suppose. But that's the issue, all right? You are, the original signal, everybody would believe, is imperfect. I mean, it has something attached to it. It has something that goes along with it that shouldn't really be there. How much do you take away? How much do you take away? That's the question. You have a lot of power when you have these mathematical techniques at your disposal. And the question is, use them wisely, young ones. Okay? All right. So I'll show you more such examples as we go along, but I didn't want to talk about any more sort of general properties of convolution, which I'll turn to now, without showing you how it looks in action. And you can look. I don't know whether we'll come back to this particular example when we do the DFT, but I'll refer you to it again when we talk about it, because they actually have in the Briggs and Hansen book, I think they have the data and they have a little bit more details about this. It's nice. And this is just one example of many possible examples. As a matter of fact, let's stay on the subject of filtering for just a second here. Okay, we're done now with this. You may raise the screen. Okay, thank you. This is probably one of the filtering, what's called filtering, is probably one of the main uses of convolution, and just in the kind of form that we were looking at. All right, you want to eliminate some frequencies, let some other frequencies go through. You do that in the frequency domain, and the question is, what are the consequences of that in the time domain? And there's a little terminology that goes along with this. Again, we'll come back to this topic a little later on in the class. But it's probably worthwhile saying it now. You have probably, many of you have no doubt heard this terminology and studied different aspects, different kinds of filters in different classes. And again, we'll also come back to it. But let me just say a little bit now. So filtering is often, not always, but often, almost synonymous with convolution. There are reasons for that, so-called time invariance or spatial invariance of convolution as it's associated with filters. This is not always the case, but it's like almost always the case. And the idea is that the filter is defined by sort of a fixed function that you're convolving with, or in the frequency domain, a fixed function that you're multiplying the Fourier transforms with. The inputs vary, but the filter function stays the same. So you imagine a system is a system that convolves an input which can vary, one input, another input, another input with a fixed function. With a fixed function or fixed signal, and the fixed signal is called the impulse response. Again, for reasons which we will understand a little bit more when we have a little bit more information about delta functions and linear systems and so on. But there's no reason why I shouldn't learn the words now. That is to say, a filter, when it is given by convolution, is of this form. Say G is equal, let me use slightly different notation now, is F convolved with H. So the idea here is F is the input. That can vary. You put different inputs into the system. H is fixed, and that's called the impulse response. And then what results from that is the output. All right? Now, again, that's the picture in the time domain. The picture in the frequency domain is what you really think of most often when you're designing filters to accomplish a certain purpose, because the picture in the frequency domain is much simpler. It's just multiplication. So in the frequency domain, that is to say, taking the Fourier transforms, let me use the uppercase notation here. You write this as, say, G of S is equal to capital F of S times capital H of S. And in this context, capital H of S is always called the transfer function, and it's always written as capital H. I don't know why, but it always is somehow. So capital H is called the transfer function. Sometimes called the system function. I'm a little hesitant here actually because I'm not sure sometimes whether this terminology applies to the time domain or the frequency domain. Certainly in the frequency domain it's called the transfer function. I was going to say it's sometimes called the system function, but I'm not sure if that refers to capital H or little h. Transfer function. All right. So to design a filter then is often to design the appropriate transfer function, to think about things in the frequency domain. And it's an art as much as it is a science. So to design a filter is to design H, the transfer function. All right, and then let nature take its course. Multiply in the frequency domain, convolve in the time domain. So for example, the low-pass filter is a very simple cutoff. Low-pass is multiplying by a rect function. I won't specify the width here, all right? But the idea is just multiply it by a scaled rectangle function of a certain whatever the appropriate width is, all right? And again, the height is 1 here, so I'm multiplying just by 1, so I'm not changing it at all in the range where the function is 1, where the function is non-zero, and then it kills it off completely outside that. Now the problem with a low-pass filter, this is called the ideal low-pass filter, because it's a sharp cutoff, all right? It cuts it off exactly at the frequency. All right, now you can achieve that actually digitally. You can't achieve that in analog form. You can't wire this into a circuit that's going to give you a sharp cutoff. So what people sometimes do is they have a gradual roll-off. There are also consequences to cutting off very sharply as opposed to cutting off sort of more gradually. And we will talk about some of these things. Although they get very specialized and it gets very, like I say, into sort of high art and the occult, I think. So we're only going to go into it to a certain extent. But it's certainly simplest to think about the ideal cases. So the ideal low-pass filter is when you just multiply by a rect function, and then the consequence in the time domain is just convolving with a scaled sinc function. All right, it's not hard to say, certainly, and at least in the frequency domain, it's not hard to see what's going on. Other possibilities, again, without spelling it out, is the high-pass filter. All right, a high-pass filter would be to pass the high frequencies and filter out the low frequencies. All right? So, for example, actually, why would you want to have a high-pass filter? What's an example where you would want to only keep the high frequencies and eliminate the low frequencies? Actually, I'll give you a hint. It comes up a lot in imaging problems. Pardon me?
Edge detection?
Edge detection, exactly. In an image, we're going to talk about higher dimensional Fourier transforms and so on, but just imagine that edges are determined by a very rapid change of either light or dark, or some rapid change in the picture, in the image. That's accompanied by, or that's characterized in the frequency domain in the spectral picture by very high frequencies. So if you want to emphasize the edges, whereas just sort of a placid scene, there's not much variation in the shading, not much variation in the intensity. An edge is a very rapid variation in intensity, say from black to white. Whereas just the ordinary scene, this desk or something like that, might not have much of a variation. So if you want to emphasize the edges, if it doesn't have very much variation, that would be typically low frequency. You want to kill those off and then emphasize only the high frequency. All right, that would detect the edges in an image. What is the transfer function look like for a high-pass filter? What sort of function would I multiply the spectrum by to keep only the high frequencies, but to kill off the low frequencies? Well, to multiply, to do that, once again, to keep the high frequencies but to eliminate the low frequencies, I would have the function be 1 from a certain stage on. And I'm keeping everything symmetric again because remember, mathematically, we have both positive frequencies and negative frequencies. All right? So again, there's a sort of a cutoff here, a cutoff frequency, nu sub c and minus nu sub c. The function would be 1 going out, ideally to infinity, from nu sub c and going out to minus infinity, and 1 down here out to minus infinity, and then it'd be 0 in between. All right? And you can easily write down a formula for that function. You can take a couple of rectangle functions and stretch them and subtract them and do all sorts of stuff with them, and it's not hard. I won't do it, but I actually do it in the notes. Okay? There's some extra complications that come into this because this thing doesn't have such an easy Fourier transform. Actually, delta functions come into this. All right? So this is actually a little bit more although the transfer function looks pretty simple, the effect in the time domain is a little bit more complicated, all right? And we do not quite have the technology yet to deal with it. But at least at an intuitive level, understanding what you want to do, it's easy enough to draw the picture, all right? That's fine. And another possibility would be a bandpass filter where you pass a range of frequencies and you eliminate all of the frequencies outside that band, all right? And again, it's not hard to draw the picture of what that should look like in the frequency domain. If you want to pass a band of frequencies, then you want to multiply by a shifted rectangle function that has only a certain extent. All right? So, and again, because the frequencies mathematically are both positive and negative and symmetric about the origin, I multiply by the transfer function for a bandpass filter would look something like this. All right? So again, it has height 1. So I'm just multiplying by 1 within a certain band of frequencies, whatever they are. I won't label the axis here. All right, here's 0. And it's 0 elsewhere. All right? So I multiply the Fourier transform of the desired signal, the filter that I want to signal, by a function that looks like that. That keeps only the frequencies in a certain band of frequencies, and it kills off the rest. And then I take the convolution in the time domain by whatever function has this Fourier transform. And that's not hard. All right? You did a homework problem on the modulation theorem. You know how to get the Fourier transform, or the inverse Fourier transform of a signal that looks like that. Okay? Not so bad. It's not so bad. And it's extremely important. All right? The whole idea of filtering, the whole idea of computing convolutions in the time domain to see what happens to the signal, whether discretely or analog, is a big industry. Okay? Okay. Now, so for right now, actually, I'm not going to say too much more about filters. Some explicit formulas are given in the notes, but the main idea that I wanted to get across was really the ease of it, and the ease of it when you think of it in the frequency domain. It's not so easy when you think of it in the time domain. And that's really the next thing I wanted to talk about. All right, so of course, you can be more or less sophisticated, but at least at the level we've been talking about, which really covers the essential ideas, it's easy to understand filtering, or what you're trying to get at. That is to say, convolution in frequency. Not so easy in time. All right? And that leads me to the next sort of important thing I wanted to say about convolution in general. Now, I do want to talk a little bit about about convolution in general, okay? Some of the properties of convolution in general. And I guess the first one is, how do you interpret convolution? All right? Well, no, before I do, let me talk about visualizing. So it's not so easy in time. So to see what happens to filtering in time, you would need to do this, you would need to visualize, right, f convolved with h, where h is whatever the given impulse response, the Fourier transform of the transfer function, or the inverse Fourier transform of the transfer function. Say that 5 times fast. The inverse Fourier transform of the transfer function. Okay? You need to visualize convolution. Now, I don't recommend this. All right? I felt like I had to say a little bit about it in the notes, but many books spend many pages and probably insist on you spending many hours on trying to visualize the convolution of 2 given functions. And the phrase you hear is flip and drag. Right? Well, visualize that, visualize this, buddy. I mean, I think it is an idiotic waste of brain cells and time to sit in a dark room quietly trying to visualize convolution. All right? Remember when I said it was idiotic to try to visualize when 2 functions were orthogonal, you know, in terms of the inner product? Well, I think it is equally idiotic to try to visualize convolution. I think the way to visualize convolution, if there is a way, is to think in terms of multiplying in the frequency domain. I mean, one of the things you start to build up is a certain amount of intuition about what Fourier transforms look like. And it's not so hard, or it might not be as hard, to visualize the product of a couple of Fourier transforms. And then again, maybe if you know what the spectrum is like, you have some sense of what the signal is like. But you tell me the truth. You be honest with me. Do you think that you can really visualize the convolution with the sinc function? I mean, for the low-pass filter, the product in the frequency domain is very simple. It's a multiplication of the rectangle function times the signal. All right. In the time domain, it's a convolution of the sinc function with the signal. That looks like, you know, sinc of x minus y, f of y, dy. All right, for a given function f. Now you know what the sinc function looks like. You trying to tell me that you can flip and drag this thing and visualize what this thing? I don't think so. All right, so don't even try. There, I've said my piece. Let me just say, hard to visualize, a challenge. All right, so I like to think that I have allowed you to put that burden down. Don't do it. Now, if you can visualize it, though, a fair question is, can you interpret it? All right. Is there sort of an interpretation, a natural interpretation of convolution that will lead you to know when to apply it, when you should expect to see it, what sort of features you should expect to see? All right, so you can't visualize so easily. Convolution easily. Is there a good interpretation? All right. How do you think about convolution? What is convolution really? All right. I mean, you can write down the formula as the integral, but you know, how do I think about that? All right. Now, I want to offer you a little bit some advice, but I also want you to be certain. I want to exercise a certain amount of caution in this. Convolution is a really pretty general operation, and it comes up in a lot of different ways. All right. I think it would be a mistake to try to attach to convolution a single interpretation. All right. Sometimes you see that sometimes, and people try to do that. But I think the fact is that it's one of those things that you get used to using, and you use it in different ways, and consequently you interpret it in different ways. I think the best thing to say is that convolution is what convolution does, and you get used to using it in so many different ways that you will automatically somehow attach the appropriate interpretation when called for in the appropriate setting. All right, so it's used in many ways. It's not subject to a single interpretation, I would say. And you do yourself no favor if you try to peg it only one way. I think it's somewhat analogous here, and I think I may have mentioned this earlier in the class, to the idea of a definite integral. I mean, you learned the definite integral when you were learning calculus by typically a simple motivating problem like the area under a curve, something like that. But you don't always think of the integral as the area under a curve. If you always try to think of the integral as the area under the curve, you do yourself no service, because in some cases, in some problems where the integral is called for, it's not called for in the context of finding the area under a curve. All right, it's called for in some other different context. All right, well, the same sort of thing happens with convolution. It's not always called for in one particular, it may be called for in different contexts. All right, so to try to attach one interpretation to it, I think, is a mistake. You use it often enough, you use it in a lot of different settings, you get very used to it, and you get very used to sort of thinking about it and thinking about it in different ways. Now, I will, having made that big plea, I do, however, I think want to offer a maxim that is often helpful. Not universal, but often helpful for the way convolution comes up. You know, so I feel like I'm retreating a little bit from this strong statement that it's not subject to an interpretation and you shouldn't really think about it that way. I think it is fair to say that in many contexts, convolution is interpreted or arises in the context of smoothing or averaging. All right? Context convolution is associated with smoothing or averaging. Now, even that is not, again, universal. All right? The low-pass filter smooths. The high-pass filter does not smooth. All right? But actually, the difference between the two, mathematically, is the low-pass filter involves convolution with a function. The high-pass filter involves convolution with distributions or delta functions, and that's not a smoothing operation. But convolution with a function is often associated with smoothing or averaging. Eliminating the jaggedness in data, like we did with the turbidity, can be thought of as smoothing the data, or it can also be thought of as averaging the data. You replace a sharp jump by an average value, all right, between the two jumps. And we're going to return to that when we talk about systems. All right, so again, even this has to be qualified somewhat. But again, we don't have the sort of technology yet at our disposal to make that too much more precise. Although I will say a little bit more. But again, we're going to see this all different aspects of this really all throughout the different topics that we talk about in the course. Almost everything we do is going to somehow touch convolution or vice versa. All right, it really is that important an operation in the whole context of Fourier analysis. All right, but in general, I'd say if you're looking for sort of an aphorism, if you look at the convolution of two functions, f convolved with g has together, the convolution has the best properties of f and g separately. All right? Or you might even say that f convolved with g is better than, is at least as good as f and g separately, and it's often better. All right? F convolved with g is usually smoother than f and g are necessarily b separately. All right, now again, this holds for, like all aphorisms, there are exceptions to it. It only holds sort of when you're talking about functions. The cutoff is when you're involved with a delta function where nothing changes at all. But for functions, the convolution of two is generally smoother than each. I'll give you an example of this. I'll give you several examples of this. So one example is if I take the rectangle function and I convolve it with itself, I get the triangle function. Now, there's a problem you have to work on this actually with a scaled rectangle function, where you actually have to compute this by evaluating the integral. All right, that, as we actually have to do once in your life, and probably only once in your life, you should compute a couple of convolution integrals and see how it works out. I'm not asking you to visualize it. I'm asking you actually to compute the integral and to show that according to the formula for convolution is integration, the convolution of a rectangle function with itself or a scaled rectangle function gives you a scaled triangle function. All right, now, why do I say this is an illustration of this property, that f convolved with g is smoother than f or g separately? Because both the rectangle function is discontinuous, the triangle function is continuous. All right? It averages it out. You've averaged out that jump that the rectangle function takes and actually made a continuous function out of it. So these are discontinuous on the left-hand side and continuous on the right-hand side. Okay? And by the way, from this formula and from the convolution theorem, and I promised this was coming, and I know mentioned it in the notes, the Fourier transform of the convolution, of course, is the Fourier transform is the product of the Fourier transforms. And the Fourier transform of the rectangle function is the sinc function, so this is sinc squared. And that is a very rapid, very quick proof that the Fourier transform of the triangle function is equal to sinc squared. That's the other reason why the Fourier transform of the triangle function is sinc squared. Okay? Now, whether or not that's really a simpler proof, I'm not so sure. You could calculate the Fourier transform of the triangle function by direct integration, right? And that's not that much involved in it. Whereas discovering convolution, proving the convolution theorem, establishing by hand that the convolution of the rectangle function with itself and the triangle function, and then concluding that the Fourier transform of the triangle function is sinc squared, well, that's a little bit of a long route. Even as fast as I talk, it took me a long time to say. Okay? So whether or not it's a simpler way of doing it, I don't know, but at least it's a nice sort of consistency check, and it sort of explains why something like that should be true. Another example of this, maybe even a more striking example that comes up, is with regard to differentiability. And again, you have a couple of homework problems on just these sorts of properties of convolution, actually, about periodic functions, convolving periodic functions to produce periodic functions, and so on. And all that is by way of getting you to think about the fact that what properties the individual functions have are inherited by the convolution, or in some case enhanced by convolution. Another is if, say, f is differentiable function, but g is not, then the convolution is differentiable. And you can say what its derivative is. Actually, the derivative of the convolution is I put the derivative on f and take the convolution. It's f prime convolved with g. Okay? And same thing for higher derivatives. All sorts of really interesting, cute, wonderful formulas and properties like this hold. All right? Similarly with higher derivatives. Of course, if both f and g are differentiable, then that's fine. And then I can put the derivative on either one. But the idea here is that you can take a non-smooth function and convolve it with a smooth function, and the result is smooth. All right? And not only that, it tells you how to compute the derivative. The derivative of this new differentiable function, f convolved with g, is f prime convolved with g. It's nice. All this stuff is just great. It's just beautiful. All right, I am, of course, skating over a few things here. There are always issues. The convolution is defined by an infinite integral. There are issues about convergence of the integral, and so on. Those are real issues. But again, the rigor police are banned from this room until I let them back in. I will let them back in to some extent a little bit before too long. I have to. But for now, just think of this formally, and to get some practice, get some ideas with using the properties and using the formulas, because it's really just great. Okay? All right, let me finish up today, and we're going to talk about more properties on Monday, more applications on Monday. But let me finish up today with another important area where convolution is applied. And actually, it harkens back to the work we did with Fourier series, where we first met convolution there in connection with solving the heat equation for heating up a ring. And I want to show you how convolution again arises in the context of the heat equation, but this time we'll just do it along a straight line. All right? And you'll see how quickly convolution leads to the solution of the equation. All right, so I want to talk about convolution of differential equations. To do that, I need a general formula here. We need what's sometimes called the derivative theorem for Fourier transforms. So this you can think of as a general property of Fourier transforms. And again, I'm not going to write out all the assumptions very carefully here, but it says this. It says if you take the Fourier transform of the derivative of a function, it is 2 pi I s times the Fourier transform of the original function, f of s. Let me put my variables in here. The Fourier transform of f prime at s all right, is 2 pi is times the Fourier transform of f at s. If the function is differentiable, then it has a Fourier transform. And again, there's a certain amount of things here that I am sweeping under the rug, but that's the main thing to understand is that the Fourier transform turns differentiation into multiplication. If you're looking for an interpretation of this in words, something you can repeat and mention to friends in passing, it would be that the Fourier transform turns a differentiation into multiplication. This is a fundamental property of the Fourier transform and is really one of the reasons why it comes up in a lot of different applications, beyond what we're going to talk about right now, but it comes up quite often. And similarly for higher derivatives. The Fourier transform of the nth derivative is 2 pi is to the n, ordinary power, this is the nth derivative, times the Fourier transform of the original function, f. Okay? Now, let me show you why that's true very briefly, all right? And I'll only do it for a special case. It actually holds quite generally, but let me give you a derivation. Just the formula for the first derivative. In the case when I know the function f of t tends to 0, say as t tends to plus or minus infinity. As it turns out, you can actually prove it more generally, but if you make this assumption, it's a very quick derivation. It follows quite easily from integration by parts. All right, so how do I take the Fourier transform of f prime at s? And as you've heard me say many times, you have no recourse here other than to appeal to the definition. Definition of the Fourier transform is the integral from minus infinity to infinity of e to the minus 2 pi I st f prime of t dt. All right? Well, look at that integral, and geez Louise, I mean, if that doesn't call out for integration by parts, then nothing does. All right? It's something times the derivative of something else, and for God's sake, integrate that by parts. So that is to say, if I let u equal e to the 2 pi minus 2 pi I st and dv equals f prime of t dt, then what happens if I integrate this by parts? My best trick. I can usually catch it in the air. If I integrate this by parts, then I get f of t times e to the minus 2 pi I st evaluated between minus infinity and infinity. All right. Minus the integral of v du, so that's minus the integral from minus infinity to infinity, f of t times du gives me a minus 2 pi I s, I'm differentiating with respect to t, times e to the minus 2 pi I st dt. All right. Now, this term is, by our assumption that the function tends to 0 at plus or minus infinity, this term is gone. All right, the boundary terms are gone. And all that remains is the integral. But the integral, that 2 pi is, the minus signs cancel, minus a minus. And that 2 pi is comes out of the integral as a constant with respect, when I'm integrating with respect to t. So this is 2 pi is times the integral from minus infinity to infinity, e to the minus 2 pi st f of t dt. And so that's just 2 pi is times the original Fourier transform, the Fourier transform of the original function. That's all there is. Okay, that's all there is to it. So it's not hard, all right? It's not hard, but it's an extremely important property. So once again, the aphorism that goes with it is Fourier transforms turn differentiation into multiplication. Okay. Now, let me show you how we're going to use this. I don't know if I'll quite finish this today. But I want to give you the setup. So let's go back to the heat equation, all right? But this time I'm going to consider the heat equation on an infinite rod, essentially the real line. Okay? So I'm going to do the heat equation on an infinite rod. All right? Once again, the heat equation says that, so U of xt is the temperature at a point x at time t, all right? And I'm given the initial temperature, all right? The rod is heated up to some initial temperature. That's U of x at 0. That's, say, f of x. No periodicity assumptions here or anything, right? It's just everything takes place on an infinite rod. So essentially the real line. Okay? And the problem is find U. Now so use the temperature. U is governed by the heat equation. And the heat equation, or the diffusion equation, so the heat equation says U sub T is equal to 1/2 UXX. That's the one-dimensional heat equation. And the 1/2 is there is just chosen to make the just for the calculation, just for the constants. Ordinarily, for the general heat equation, there would be a constant in here depending on the nature of the rod and so on. All right? Okay. Now, again, U is a function of two variables. On the left-hand side is the derivative with respect to t. On the right-hand side is the second derivative with respect to s. What I'm going to do is I'm going to take the Fourier transform of both sides of that equation with respect to x, with respect to the spatial variable. Okay, I want to take the Fourier transform in the spatial variable. All right? So if this might be a little bit easier, if u is lowercase u is the original function, then the Fourier transform I'll call capital U of st. So again, the t is sort of just tagging along for the ride. It's the spatial variable that I'm taking the Fourier transform with respect to. Okay? So what about the left-hand side? What is the Fourier transform of u sub t? So that's the integral from minus infinity to infinity of the derivative e to the minus 2 pi I st, the derivative ddt of u of xt dt by definition of the Fourier transform. And you see here I'm differentiating with respect, dx, he said to himself. So I'm taking the derivative with respect to t here. I'm integrating with respect to x, so this derivative comes out of the integral. That is, I can write this as ddt of the integral from minus infinity to infinity of e to the minus 2 pi I st u of xt s. I got sorry. S. I knew there was something wrong here. Sx. There. Now everything is kosher. Sx dx. You got to be so careful in this business. Just kills me. All right. Okay, now everything's okay. I'm taking the Fourier transform with respect to x. I'm calling a spatial variable x. The Fourier transform is e to the minus 2 pi I sx. If I take the Fourier transform of the time derivative, that's this. I can pull the time derivative out because the only thing that depends on time here is this u. All right, now that I've got my variable straight. And so that is ddt of capital U of st. All right, that is the Fourier transform of the spatial variable of the time derivative is just the time derivative of the Fourier transform, if you want to say it in words. Okay, so that's what happens to the left-hand side. What about the right-hand side? Well, the right-hand side of the heat equation, I use the derivative theorem. I have two derivatives, the second derivative with respect to x. If I take the Fourier transform of the right-hand side, then what comes out is a factor of 2 pi I s squared. So the Fourier transform of uxx, again with respect to the spatial variable, is going to give me 2 pi I s squared times the original Fourier, the Fourier transform of the original function, undifferentiated at st. Again, t is sort of going along for the ride here. It's the transform in the spatial variable that counts. So that's minus 4 pi, I squared is minus 1, so it's minus 4 pi squared s squared, capital U of st. All right? All right, so plug into the heat equation. There it is. Plug into the heat equation. ut equals 1/2 uxx transforms to cap ddt, I'll just use a single variable, ddt of u st is equal to minus 2 pi squared, there's a 1/2 out here, so minus 2 pi squared s squared times u. X, S. And ST. All right? Now look at this, kids. That's an ordinary differential equation for capital U. It's a derivative with respect to time. All right? This is a constant as far as time is concerned. It's dt of u is equal to a constant times u. What? is the solution. The solution is u of st is equal to u of s0, the initial condition, times e to the minus 2 pi squared s squared t. Because anybody can solve that equation. Your little brother and sister can solve that equation. Okay? Now, what is us0? What is us0? That is the Fourier transform of the initial condition. That's the integral from minus infinity to infinity of ux0 e to the minus 2 pi I sx dx. ux0 is the initial temperature distribution f. So that's the integral from minus infinity to infinity f of x times e to the minus 2 pi I sx. That's the Fourier transform of f. Let's call that, say, capital F of s. Okay? All right. So what is capital U in terms of all the data that I have? Everything now is sort of known. We're almost done. I might be able to finish it. So is there a class waiting to get in here? Screw them. All right. So, excuse me. So U of Sx is equal to F of s times e to the st, God. F of s times e to the minus 2 pi squared s squared t. All right? The Fourier transform of the right-hand side is the product of two functions. All right? The Fourier transform is the product of two functions, the product of this Gaussian with the Fourier transform of the initial data. What is the solution? The solution is the convolution of the two. All right? Now, you have to recognize, one knows what happens to the Fourier transform of a Gaussian, actually. That is, the Fourier transform of, so I'll just give you this fact. The square root of 1 over the square root of 2 pi t times e to the minus, I want to get my constants right, e to the minus x squared over 2t. You have to use the scaling theorem here, and that's all that's involved. The Fourier transform of this is this, equals e to the minus 2 pi squared s squared t. Okay, that uses the fact the Fourier transform of the Gaussian. I think we really got to go. All right, so what is the actual form of the solution? The form of the solution then is u of xt is the convolution. This is so cool. It is f of x convolved with that function, e to the minus 1 over the square root of 2 pi t e to the minus 2 pi squared e to the minus x squared over 2t. All right? Convolution comes into the solution of differential equations because often in solving differential equations, if you take the Fourier transform, differentiation becomes multiplication. Multiplication in the frequency domain becomes convolution in the time domain. All right? On taking the inverse Fourier transform. So in the time domain, I'll write this integral out next time more fully just so you get the full power of it. It's the convolution of the initial data with this, what's called the heat kernel for the infinite line, or for the rod. All right? And that's lightning fast how the heat equation is solved. All right? And how convolution comes in a very fundamental way. And that's it for today. For Monday, I'll say one more thing. We're going to talk about the central limit theorem. It is a real gem and a real jewel in this class, I think, to see how convolution applies to that theorem. So read over that material very carefully over the weekend so I don't have to do a lot of background on probability. All right? We are done. Thank you all. Bye.